All right, let's look at this example. A certain investment fund yields a 7.9% annual return. Assume this yield continues into the future. First of all, it's worth noting that 7.9% annual return is pretty dang good, and if that keeps up from year to year, that's very good. Anyhow, so what is the fund's 5-year growth rate? All right, so this is our annual growth rate. That's 0.079 if we're going to do any computations with it. If we want to convert this to a 5-year growth rate, let me pull up the whiteboard. So 7.9% annual. So first of all, we need the factor. So R is 0.079, and therefore B is 1.079, and that's the factor, the annual factor. Okay, and so essentially what we're going to do is raise b to the 5th power, and this will become our 5-year factor. And then we will, I'm going to put an arrow here to indicate the process. And then we're going to convert this 5-year factor to a 5-year rate. And the way we do that is we subtract 1. And then finally, to put it in percent form, that's supposed to be a percent sign. Let me try that again. We multiply this by 100. Okay, so let's do all that. So we're going to start with our factor, our annual factor. We'll raise that to the 5th power. Then we'll subtract 1. And finally, we'll multiply by 100. And we get 46.25%. Okay. So that is our 5-year growth rate. What about the fund's doubling time? How do we find that? Well, again, this is a calculator problem. And so I want to know how long it takes me to go from any given amount to double that amount, but I need the function. I actually need the model in order to find this doubling time. And so we don't really have much information here except for this annual rate, but that's okay, that's enough. We do, however, need to assume that we have some initial value. So just to make things easy, I'm going to assume that my initial value is 1, and then my factor is 1.079 raised to the x power, and that's going to be my model. And so the nice thing about assuming that we started with $1 is that I just need to go to $2 to get my doubling time. And it doesn't matter because no matter what we put in, the doubling time will be the same. Okay. All right. So let's now look at our window. And I'm going to take a chance that my that Zoom Fit will do okay with my window as it was. It was 0 to 25. So we'll see. If it's not, then we can look at the table and make it better. But this is okay. So we'll do calc intersect, and we get our intersection to be 9.12. All right. So let's move on to part C. Suppose you decide to open a fund account by making an initial deposit. If your goal is to grow to $2,500 in 3 years, what should you deposit today? Okay, so this is a different kind of question than what we've had before, because what we're talking about now is we have a target output that we want to get to, and we want to get there in a certain amount of time. So the unknown, we have a different unknown. The unknown here is the initial value, or the initial investment. So I'm going to actually write this out in equation form so you kind of get a better idea of what it is that we're working with. So if we want to get $2,500 in 3 years' time, then my initial value, I'm going to call that A sub 0. And there's my factor. And I know that that's going to be 3, right? Because T is 3 years. So you see how this is a different unknown that we're looking for. This is the thing that we're trying to find. So I'm going to just solve this algebraically. I'll still go to the the calculator to actually get the value, but that's what I'm going to need to compute right there. 2,500 divided by 1.079 to the third power. So let's get the calculator. And I want to be careful with my parentheses here and make sure that the only thing that gets cubed is the denominator here. Okay, so that's what I need to put in, $1,990.10. Approximately. And that should get me $2,500 in 3 years. Okay. So here's our answers. These answers go into things in a bit more depth than what I did, but we did arrive at the same values pretty much the same way. Okay. Here's a population model about Las Vegas, and it says the city of Las Vegas, Nevada experienced exponential population growth between 1960 and 2000. According to the U.S. Census, Las Vegas population was 64.4 thousand in 1960 and 478.4 thousand in the year 2000. Use this data to find a model P equals P of T that gives the population of Las Vegas in thousands as a function of the number of years after July 1st, 1960. Okay, well, hold on a second. This is different. This is a different kind of problem, isn't it? We are given data and asked to write the function, but we are not normally, in order, like what we've done up to this point, is to write an exponential function. I gave you a rate or a factor. I gave you an R value or something that you could use to get it, or a doubling time or something like that. But that's not what happened here. Instead, I've given you 2 points. This is also an elapsed time model. Just pointing that out. And our 2 points are 0 and 64.4. And secondly, 40, because we are in the year 2000, which is 40 years after 1960, and 478.4. So here's the idea. I've got this point at 64.4, and then 40 out here, I've got another point which is 478, and there is some exponential function that passes through those 2 points, and I want to write the equation of it. Okay. But we don't specifically know how to do this yet. All right, well, let's talk about how we could figure this out. So we want an exponential model, as this says, whose value at time 0 is 64.4 and value at 40 is 478.4, which is what we just wrote on the other slide. Let's look at the ratio P40 to P0. So the value of the population at 40 and the value of population at 0. Now, that's going to be, that's 478.4 divided by 64.4. That's going to be my 40-year base. So in other words, that's like my growth factor. Okay, so as I was saying, that is my growth factor. Specifically, it is my 40-year growth factor. And just in general, whenever you have an exponential function, and if I have two outputs of the function, now just remember what the definition of the growth factor was. It was if I go over 1 unit, it's how much I go up, right? That ratio of sort of the rise over the run. Sorry, I'm having some computer troubles here. As I was saying, we're looking at this 40-year growth factor. So if you recall, we looked at a table a few slides ago that had we were computing 5-year growth factors, and we would compute the ratio of the function output when we jump forward 5 units. So this is the same thing. It's just that we're jumping forward 40 units. And so that's 478.4 divided by 64.4. So that's great, right? But we actually want the regular non-40-year growth factor. We want the annual growth factor. So we need to convert this thing to its annual factor. So what do? Well, we just need to raise this. This is a little weird, but this is what we do. We have to raise it to the 1/40th power, because this is the 40-year growth factor. So if we want to convert this to annual, we raise it to the 1/40th. Okay, so we take 478.4 over 64.4, raise that to the 1/40th, then all of this mess in here is now b. And so if you can sort of zoom out a little bit, we have initial value times b raised to the t. And that is the form of the exponential function. So that's what you see right here. Now, in this next equation, all we've done is we've taken this form and done a little bit of algebraic manipulation, rewriting things. So we combine these two exponents by multiplying, and we have this nice form. And so what we have just done is kind of roughly talked about how you write the equation of an exponential function that's passing through 2 points. Let me go to the relevant slide. We'll go back and finish the problem in a moment, but here's what we just did. So the formula is we started with the initial value of an exponential function, f of 0, or f at time 0, and then we took the value n units later, and that's f of n. And so these are our 2 points, 0 and f of 0 and n and f of n. This notation is just because a little easier to write. Then the exponential function that passes through these 2 points is given by this formula. And I don't want you to think that every time you use this, you have to write this entire thing out. The formula is over here. That's the formula. It's just that sometimes, what's the benefit to having it in this form is that here I can clearly identify that all this in the middle here, without the x, that's my b value. Whereas in this form, it's a little harder to see what the growth factor is. But yeah, so that's how we write the function, okay, when we are given 2 points. Anyway, this is one method. There is another method which we'll introduce later, but this is one method. Okay, so now we can go back and actually talk about that model. So we have that model, there it is. And now I want to answer some questions, which we will do in the next video.